All right, we are going to talk about the vector equation of a line. So we're used to Cartesian equations of lines, y equals mx plus b, but there's a couple other ways to represent a line, and one of them is using a vector equation. So the vector equation looks like this, and it's very similar in the sense that it gives you a point, and we call this the position vector, and it's kind of akin to our b value, our y-intercept. It kind of gives you a starting point. Okay, so it gives you a position vector, that's a point that is on the line, and then it's plus t or some parameter. It doesn't matter, it doesn't have to be t, it can be any letter there, but t is typical, or lambda you'll see sometimes. And then it gives you a direction vector, and it's basically your slope. Okay, so you have a position vector and you have a direction vector, and that makes up your equation of your line. So it's very similar to y equals mx plus b. It's kind of the same sort of form, except your y is actually a vector xy, your b is actually a point, okay, a position vector, and your b here is your slope vector, so it's delta x and delta y. So that's what the vector equation looks like. All right, so you have your Cartesian equation, you remember, is y equals mx plus b. You have your vector equation, which is r equals a plus tb, and then you have what is called a parametric equation. Okay, and basically a parametric equation is something where you're given the vectors in parameters. So you're given things in terms of a letter. So you're given like x is 2 plus 4t and y is 20 minus 3t. We're not going to go into the whole question here, but this is kind of the idea of a parametric equation. All right? So you basically have three forms. Okay, you have your Cartesian equation, you have your vector equation, and you have your parametric equation. Okay, so let me go back up here just for a second to look at this question for a second. It gives you a point, it starts at 220, this yacht does, and it's moving at 4 and minus 3. Okay, so the way that you get the vector equation from that is your position is 220, and your direction that you're moving is 4 and minus 3. So that is your vector equation. To go from that, you kind of treat this r is actually the vector xy. Okay? So we can go from that to our parametric equations by x is 2 plus 4t and y is 20 minus 3t. Okay? And then you can go to your Cartesian equation from that. All right, there's our parametric equations. We can go to our Cartesian equations by solving those for t. So in other words, we have x is equal to 2 plus 4t. So we have x minus 2 divided by 4 is equal to t. And then we have y is 20 minus 3t. Is 20 minus 3t. So you get y minus 20 divided by minus 3 is equal to t. And then you can set those equal to each other, so you have x minus 2 over 4 is equal to y minus 20 over minus 3. And you had that is technically the form of a Cartesian equation because it's x and y, but it looks a little funny. So we can make this minus 3x plus 6. We just multiply the minus 3 up there equals 4y minus 80. If we multiply the 4 up there, and then you can solve that by going minus 80 comes over and becomes plus 80 plus 6 is 4y plus 3x. And so you can get your Cartesian equation by saying 3x plus 4y is equal to 86. So what you have is that's your Cartesian equation. Your vector equation is r is equal to 2 and 20 plus t onto 4 and minus 3. And your parametric equations are x is equal to 2 plus 4t and y is equal to 20 minus 3t. So there's three different ways to represent the same thing. This is Cartesian. This is what we're used to. This is the vector equation equivalent of that Cartesian equation. And then these make up our parametric equation. Okay, so three different ways to represent the same thing. When you look at it in 3 dimensions, it looks very similar. So you have a Cartesian form as ax plus by plus cz now, because there's a third component, equals d. That's a plane, and a plane is basically just a three-dimensional, it's like a flat surface that stretches out into a third dimension. So you kind of have a rectangle that goes to infinity. That's what a plane is. Vector form looks like that. Parametric form looks like this. Okay, so very similar. It's just, you just flip everything into three dimensions, so you add a third component. All right, and if you look at a Cartesian equations, you're sometimes going to see them written like this, so they're not actually solved like x, y, z. They just look like this, where x minus something over something equals y minus something over something equals z minus something over something. Okay, and those a's and b's correspond up here. This, if you kind of think about it this way, this right here, if you circle these and make it into a vector, that's your position vector, and this is your direction vector from up here. Okay, so that's the idea behind the vector equation of a line. So here's an example. Find the vector equation and the parametric equations of the line through this point and in this direction. So in order to find the vector equation of a line, you need the position vector. This is the position vector, 1, minus 2, and 3. That's the position vector. This is the direction vector. Okay, so this position vector goes first, and then the direction vector goes second, and it's multiplied. The direction vector is always multiplied by a parameter. From that, you can get x equals 1 plus 4 lambda, y equals minus 2 plus 5 lambda, and z equals 3 minus 6 lambda as your parametric equations. Okay? And if you want a Cartesian equation, you would then just solve each of these for lambda. So you go x minus 1 over 4, okay, equals y plus 2 over 5 equals z minus 3 over minus 6, okay? And if you wanted to, you can switch that last one. You can sort of flip the sign so it's not divided by minus 6. But that's your Cartesian equation. So vector equation, parametric equation, Cartesian equation. That's how it works. All right, here's another example. It says find the parametric equations aligned through these 2 points. So we start out, we want to find the direction vector. The direction vector is the vector AB. It's the position vector AB. So it's a little weird with the terminology, but you're looking for the vector AB or BA. It doesn't matter which one, but we're going to try to find AB. So we know how to do that. We just go B minus A. So minus 1 minus 2, 0 minus minus 1, and 2 minus 4, and we get our position vector AB. This position vector becomes the direction vector in our equation of our line. Okay? So what we end up with is, if we were to write our vector equation, it would be R equals, and it would be 2 minus 1 and 4. That's the position vector A plus lambda times minus 3, or 1, not 1, minus 1 and 2. Okay, that's a 1. Doesn't look much like a 1, but let's see if we can tidy it up just a bit. There we go. And then from there, we can get our parametric equations. Okay. If we use the point A, which I did, it's 2 minus 3 lambda minus 1 plus lambda and 4 minus 2 lambda. That's our parametric equation. If we want to, though, we can use the point B because it's also on the line. So we could also use the point B, which is minus 1, 0, and 2, and use that to find our parametric equation. So it would be minus 1 plus minus 3 lambda, or just minus 3. But you notice they changed the parameter. And that's because if you use the point B, that number is going to be different than that number in order to get to the same point. Okay? So both of the equations generate the same set of points, but the lambda and mu values to get a specific point are different. So I'm going to leave it there because that's really just, I'm just looking for you to understand the concept. Here are a few more questions. We'll work on these in class together tomorrow, but it's just understand the concept of parametric equation, vector equation, Cartesian equation, and working through them. All right, so that's where we're going to leave it. Hopefully that made sense, and we'll talk about it in class tomorrow.